All right.
Thank you.
Okay, thank you everyone for coming out for the weekly seminar. Apologies for not having snacks for the talk. So, which is great because that means everyone is here for the talk. No one is here for the snacks. So, but apologies, the university catering was not able to fulfill the order this week. So we'll get back to normal next week. And possibly be making some changes to how we're doing snacks for the seminar moving forward, but stay tuned for that. So I gotta finalize some things. So we got a Drew Thomas from Department of Energy is going to be giving us a presentation today. And I do want to point out that if you're online, and it looks like we got a fair number of online participants today. If you have questions, please either post your questions in the chat and we can moderate those afterwards. Or raise your hand if you would like to ask the question yourself. Before we get started, if you're online, please make sure that your microphones are muted, so we don't have any interruptions during the presentation. And with that, I'm gonna also, I get to introduce Professor John Gilligan, who has back full-time with the department after a stint working as one of the associate deans over at the College of Engineering, and he's going to introduce our speaker this week. So thank you.
Thank you, Steve. Thank you. Yeah, it's good to be back in the department. Although I'm on semi-sabbatical this semester and next, but I'm going to be around. I may be teaching you next fall. Who knows? Depending upon what your interest might be. So, yeah, I've been in the dean's office for the last 10 years. As the chief operating officer for the College of Engineering here. Done a great job. We've accomplished a lot of activities, getting some new awards coming to the college, hopefully nuclear as well, research awards. So everything is going very, very well. So it's really good to step down and come back to my academic home and to be with you. So, but it's only part of the job that I do. The other part, I'm the director of the integration office for the NEUP program, which is a national program which funds much of the research for all nuclear engineering departments and many others around the country. This program has been going since 2008, 2009, when I joined as director. And we're very proud of the program, and it's an exciting program. It supports all the university's scholarships and fellowships, as well as the research projects that your faculty, all of our faculty, and other departments too on campus apply for and receive. So, anybody have a fellowship out there? How many fellowship holders or scholarship holders do we have? At least a couple. I know on campus we probably have at any given time probably 10 or something like that, or more that have been funded by the program. So it's my pleasure today then to introduce Drew Thomas. Now, Drew, I'm the director, but Drew is the most important person in the NEUP program office, because he actually runs the office, makes sure everything is done properly, assembles all of the reviews for all the proposals that come in. You know, we get 600 or more pre-applications every year, plus. Each one of those has to be reviewed 3 times by faculty and experts around the country at national labs and other departments and so forth. So that's what Drew is really handling, all the details associated with all the assignment of all the reviewers and handling the panels, talking to everybody in the country. Drew knows more nuclear people around the country than anybody in this room right now. I'll tell you that right now, because he talks to everybody on a weekly or a monthly basis in terms of setting up reviews and then talking with individual faculty, department heads, and others. So, Drew, it's really important. We're very excited to have you here visiting along with Pam from the office to talk to our faculty and see the reactor. And first time here, I know. And so it's really a pleasure to have you here and have you meet all of our students and faculty. Drew has been with the program since 2011. So he started out, he's worked his way up to the manager position, which is really a key part of what the DOE strategy is for funding universities in this country. He's also chaired the Conference on Nuclear Training and Education. That's the CONTI conference since 2017. He works with Lisa Marshall on that. And also in the American Nuclear Society Education and Training Division, you've chaired that. And also the vice chair now for the American Nuclear Society Scholarship Policy and Coordination Committee. So Drew, good to have you with us.
Okay, thank you, John. All right, thanks, everybody. It's a pleasure to be with you. I have cards here, but I also, I'll explain my affiliation, but I also brought some cards of a technical recruiter from INL. If you're interested in graduate internships, postdocs, those types of things. So I'd be happy to pass this information on, and if you have any questions there, you can let me know. So thank you, John, for that kind introduction. I want to clarify one thing that John said, which is that it's actually the team, the great team of folks that I have that really do all these details. We have a small team of about 10 people that John and I included that facilitate this program, which has a budget of about $60 to $70 million a year for university research infrastructure and student support. And there's an extra $30 or so million for small business research that goes along with that. So the overall portfolio that flows through our office is in that about $100 million range. So I want to give you a little bit, for those of you that are familiar or unfamiliar with the NUP program. I want to give a couple of, a little bit of an overview of what the program is so you can understand the context of what I'm going to talk about today. And then really what I'm going to focus on is more of a retrospective look at what are called integrated research projects. They're large projects that are funded by the department. There's a few that are that I'm going to review today. One that was actually conducted here at NC State, I won't be covering today, but Professor Namdin was the PI for that, looking at reactor accident scenarios. And so these are really important projects, really unique projects for the department that I'll be visiting about today. So for those of you who have not heard me speak before, I always start with this slide. The Office of Nuclear Energy has a mission that's fourfold. That is to keep the U.S. reactor fleet operating, to deploy new nuclear reactors and advanced technologies, secure and sustain the nuclear fuel cycle, and then expand international energy cooperation. And so collectively, those Office of Nuclear Energy, I'm going to use government acronyms all over the place. So please, holler at me, wave your hand if you don't know what I'm talking about. But we call Office of Nuclear Energy NE. And so those NE sponsored activities make up the core priorities to combat climate change, to meet the administration's goals in a carbon free, carbon neutral environment. And nuclear energy is a core component, as you all are likely aware, and talking with others about, a core component of that strategy to really have a baseload energy that has multiple different capabilities depending on the technology. And those opportunities are near endless. So there's really two main programs that the department sponsors in this space. The first is the Nuclear Energy University Program. And as John said, 2008-2009 timeframe is when that university program was consolidated into one combined pot. And it covers all sorts of different Office of Nuclear Energy areas, including everything from nuclear cybersecurity to chemistry type issues with aqueous or pyroprocessing type applications for nuclear materials, covers nuclear fuels, materials, the back end of the fuel cycle when you're talking about how you dispose, transport, and store used nuclear fuel and used material. And so NEUP is kind of consolidated to have a university focus for all of those different areas. And so we're kind of the one-stop shop that covers all of those, and all of your professors here all of those different areas they're focused on have touch points with this program. There's also the UNLP program. It's the University Nuclear Leadership Program. And we facilitate the Office of Nuclear Energy side of this. You may have heard this acronym before. There's an NRC program that's a UNLP and an SA that has a UNLP program. But what we do for our UNLP program is fund community college, undergraduate and graduate scholarships and fellowships. The idea there, and one of the things that I like to highlight with graduate students and with those thinking about graduate school, is that the idea behind those opportunities is to give you some academic freedom as a student to pursue the things that you want to do in coordination with your advising professor. And I know you're all graduate students. This opportunity has kind of passed for all of you likely, but it's an important thing. As you know, one thing I like to talk about even with graduate students is you all are mentoring the undergraduate students in your labs, early graduate students, and it's an opportunity to make sure that opportunity is known. To give you an idea of the overall scope of what the NUP and UNLP programs are, we are approaching $1 billion in overall funding that's been dedicated to universities over the last 10 to 12 years. As part of that, there's close to 2,500 different awards in 45 states, 1 territory in the District of Columbia, 7 national laboratories that actively participated in these projects. There are 13 active utilities that have supported those projects in 138 different US universities and colleges. And you'll see here on my next slide, some of these universities have had multiple awards and a large amount of support over those years. So those 138 colleges and universities may have 1 award, may have 30, 40, 100 awards. It just depends on how big the program is. But I always like to show this slide because you can see from a national perspective where the program touches, and there's no region in the United States. We're still lobbying North Dakota here, but we'll see what happens there. But there's no region in the United States that has not been touched by this NUP program, and it really shows. I think this is an important point for nuclear, how multidisciplinary the nuclear engineering and nuclear energy discipline is when you think of all these different colleges, engineering programs, and otherwise that have been supported over the years. So I wanted to highlight before I get started with my full presentation, what is NC State and NUP? What are the numbers? And so the big number up there is the total number. You know, I calculated this by hand, so I'm no mathematician, so we'll see, but it's close. About $41 million since 2009 has come to North Carolina State to support students, support faculty, support really impactful research. That includes 40 research and development awards, 1 distinguished early career award, which we and 38 research and development awards, and the 1 IRP award that I told you about. There are 15 infrastructure awards. So when you look at Polestar, the reactor facility that you have, if you look at those beam lines that come out of Polestar, if you look at the upgrades that have happened to the secondary systems there, that's all been paid for through NUP funds, and the upgrades that have been seen there. There's also some significant general scientific infrastructure upgrades, including a new molten salt loop that just got awarded, that's going to be funded and going to be put in the upcoming year or 2. So I also want to point out there's been 92 student awards. Obviously, there's some folks here who benefited from that, but 23 graduate fellowships. To give you an idea, we fund about 33 graduate fellowships a year, and so 23 fellowships over the course of the program is quite impressive for an institution. And undergraduate scholarships, we have close to 100 of those combined. Really important program for us to really show that there's support for nuclear energy all the way from when you're a senior in high school all the way up through the process. So that is my little spin on the program. I want to get into integrated research projects and what these things are, and then we'll get into some technical details. I will give you a warning. I am not a nuclear engineer, so I'm going to give you a good overview of some of these projects, go into some details. But if there's specific questions, I'm going to refer you to the final report, which I have attached here. I can talk about some things. Some things are, I'm not as familiar with. I didn't do the research for these projects, obviously. I'm just going to talk to you about them. So, integrated research projects were started as part of this program in 2011. And at the time, for those who were around at that point in time, there were two assistant secretaries who were known as the Pete's, and there was a big initiative at that time to address maturing the university program, to try to provide some type of alternate model, like a consortia type model, to the research program. And so as that was talked about and internally deliberated at DOE, the idea was this integrated research project type environment, where the idea is to address technical challenges that are too large for the traditional, more incremental research that happens on regular research grants. And so they're intended to be multi-university and multidisciplinary, meaning that instead of just addressing one challenge or one hypothesis, the idea is that the IRP is supposed to cover a broader set of technical challenges and address a specific technical gap. And I think you'll see what I'm talking about as I get into some specific examples of what this is. So, and IRPs over the years have covered a variety of different areas, covered advanced nuclear materials, reactor design, safety, modeling, and simulation, use fuel disposition, to just name a few. And so it really is a cross-cutting program across all of the different Office of Nuclear Energy areas. So I'm going to talk about two examples here, and I'm hoping this gives you a good idea of some of the major impacts that the NEUP project has had. How many of you are familiar with Kairos Power? Is that a familiar name to everybody? Okay. So, so the story that I'm going to tell a little bit is a little bit about Kairos Power, their beginnings, and the IRP projects that spawned that idea. And now we have an advanced nuclear startup in the California area that's pursuing the fluoride salt-cooled high temperature reactor concept. And so hoping I can kind of walk you through the iterations of what their design process was, what the reactor type is. And like I said, I can answer some questions, but I'm going to give you some resources as well. I'm assuming that this presentation will be shared with you all. So if not, grab my card and I'll send it to you. So when it comes to the fluoride salt-cooled high temperature reactor, for those of you who are less familiar with it, it's a concept that was developed in the early 2000s, but it was executed from the Gen 4 forum, selected reactors when the Gen 4 activities were happening in 2001 timeframe. It began to gain interest in around 2004 as an actual concept, and there was some preliminary research supported through the universities and national labs for that type of concept. And for those of you that aren't familiar with the concept, it combines several kind of advanced reactor concepts or technologies, and kind of mishmashes them into, I think somebody, Charles Forsberg or Kairos Power might not be happy with me saying this, but kind of like a Frankenstein of technologies, right? Like, oh, this works well, in this situation, these types of innovations that work well here. Why don't we combine them all? The three main components of that are FLiBe as a coolant, so a molten salt coolant that's clean, meaning that it doesn't have fuel in the molten salt. A graphite matrix coated particle fuel, TRISO fuel, is what's being used in the Kairos concept. That creates a situation where you have encapsulated fuel instead of the traditional MSR concept of the fuel within salt. And then passive decay heat removal systems that create an inherently safe design that's high temperature, low pressure, and has more passive systems for heat removal for safety. So this is where I'm going to say, if I don't know the answer to the question, look at these two reports. They're both available through OSTI, and I've linked them here so you can just click on them. There's two projects that were funded through DOE, a total investment of about $12 million over the course of about, what was it? About 8 years to first test the concept and test the different pieces in this first project, which is called the fluoride salt-cooled high temperature reactor for power and process heat. And then a follow-on project that dealt with some of the issues that were emerging from the initial project, and that to focus on tritium management, materials development, and some of those types of issues. So these are several 100-page reports each. Lots of good stuff in there. I reviewed them as I was preparing this to hopefully be a little bit, so to stay pretty educated on some questions that would come up. But I wanted to talk a little bit about probably one of the coolest things out of everything as we've talked about this FHR concept. It's one of those really cool technology development type conversations. When you think about how has the technology and the technology development that DOE has supported over decades been leveraged to create a unique concept that's eventually heading toward demonstration and commercialization, if all goes well. The concept was built from several major Office of Nuclear Energy initiatives that included, the 1960s era molten salt testing and the MSR test that happened at Oak Ridge in the 60s. 30 years of ceramic encapsulated fuel research that's been performed by the high temperature gas reactor program at the national laboratories, and then extensive research at EBR2 on sodium fast reactors that successfully demonstrated this passive decay heat removal DRAX type system that's utilized in this reactor type. And so one of the maybe coolest things I think out of all of this is when you think about a $12 million investment as a university project, there's no possible way all this technology could have been developed in that time frame with that amount of money. But the FHR concept would have never matured without all of these other pieces of long-term DOE research that happens, across the board. And we had some, good on folks that are in this technical space to see those innovations and look at ways to combine them. So I want to go over a little bit about the 2011 project, and then I'll go over the 2014 project, kind of give you an overview of what the ideas were that were proposed and some of the activities that happened. The 2011 project was primarily an experimental effort to try to provide some data for both the development of an FHR and the economic case for an FHR. And so, there's a schematic here that kind of talks about an FHR with a combined Brayton cycle, and some of the reasons why some of these initial concepts were proposed in this 2011 project were included the NAC system, and then also included a heat storage system to be able to try to make an economic case for an FHR. And so that was really the original concept that happened in this 2011 project, trying to make kind of a dual argument for both the technology readiness, but also an economic case for the reactor. There were three main thrust areas for this project. One was thermal hydraulic experiments and design. Next was materials testing, and then materials irradiation was the third piece. One of the unique things about this project, and one thing that I like to highlight about it, is before the first project started in 2011, University of California, Berkeley and MIT coordinated a group of different FHR workshops. And the idea behind this was, this has never been done. It's a new reactor concept. It's developing that space, and how do we kind of get the collective brain together and try to understand what the potential issues are, where we should focus our research efforts, how do we conduct knowledge transfer. And the first workshop that they held, which I thought was really interesting, and invited I think 2 or 3 of the original individuals who worked on the MSR experiments at Oak Ridge to these conferences, got them out there. And there's a visual, there's some students that worked on the project at the time who are now university professors across the nation. I can give you names if you'd be interested, but they told me a story once about how, they had some first-year graduate students and, the original MSR developers sat in a room for a week for this first workshop, and then came back for that second workshop. And, we're really able to walk through the different design decisions and why the original experiments were conducted the way they were, how it was engineered, all those other types of things, and got some really unique stories and data that you really can't get unless you're working in the lab with somebody, to actually be able to have a little bit of knowledge transfer between, from a generational standpoint, knowledge transfer. And some of these folks have passed at this point, and it's one of those things where it was a prime example and opportunity at the time to, take the initial innovation that we had in the 50s and 60s in reactor technology and nuclear science and transfer that to folks who are actively working in the industry today. Pretty neat opportunity from that standpoint. So I'll get into the 3 different areas and describe a little bit about what happened. University of California, Berkeley created this is a combined, I think it's called the Combined Integrated Experiments Test Facility, where they created a scale, 50% scale replica of the thermal hydraulics type systems that would go into the original design here, and did a lot of testing. Now, the interesting thing here about this picture is we've got our CEO of Kairos Power, who was a graduate student at the time. And for those who know Dr. Per Peterson, who's the chief nuclear officer there, both founders of Kairos Power, and a kind of a cool story when you look back at this picture. But there are several papers that talk about this pebble bed FHR type concept, and really give a technical description of the testing facilities and of the concept as a whole, if you're interested. And then the results of the design and fabrication of this integral effects facility, if you're interested, if that's your cup of tea. Secondarily, there was corrosion and irradiation testing that happened, and this is kind of a unique environment. University of Wisconsin-Madison and MIT did the materials testing and the irradiation testing respectively. Some interesting takeaways here is that this was the first reactor concept at the time to use solid fuel and molten salt coolant. And so when you think about what that problem is, and flibe salt and the capabilities that were in the university system at the time, at University of Wisconsin-Madison, this was really a first of its kind type experimental facility to use more of a clean salt loop concept to be able to do corrosion testing on a variety of different materials. The idea here, and if you read through the reports, you'll see that there are, I gave one example here on the corrosion testing, but there's a variety of different materials that they use, really use kind of a wide ranging approach of what are the benefits and disadvantages of different materials from a corrosion perspective. to be able to understand, how materials would perform in this type of a system. Now, one of the interesting things about this type of a concept is when you talk about MSR materials, the corrosive behavior of the fuel integrated with the salt is significantly different than having an encapsulated fuel and just having the molten salt in the system. And so one of the arguments for an FHR is that you can potentially use different, less expensive materials, structural materials, because of the different chemistry and the different conditions that are there. And so that was really what they were trying to figure out. So corrosion experiments happened on 316 stainless steel, Hastelloy, 6-stick composites, like I said, a wide variety of materials, with the idea that the operating conditions for this reactor would be around 700 C, and the materials that are being tested, like TRISO fuel, for example, have melting temperatures and other things much higher than that. And so that creates that operational gap that you might need for a passive decay heat system to work, or other things like that. So the 2014 IRP project took everything a step further. So when you think about, how do you design a project, how do you design a reactor, and then how do you design a project that pushes that reactor forward to where you're actually going to build something? This 2014 IRP was really methodology for how to do that. There were six components to them, and I'll cover them a little bit more briefly, because you'll notice that we've got essentially the same structure of the project, but pushing these things in different, more advanced ways. So you can think, there was of course the conceptual design studies to talk about economics, but from a modeling perspective and from a testing perspective, it really goes the extra mile. So you can think, instead of doing separate effect testing, they started doing integral effects testing and modeling. The corrosion tests went from a more static type model to corrosion test loops to be able to see how materials degrade over time. Of course, some additional in-reactor materials testing to understand irradiation effects, and some benchmarking activities to make sure that the data that was being produced was validated along with other concepts that were similar in these different areas. So this is, at the end of the day, this is a schematic that you can see on Kairos's Kairos Power's website. And this is the final concept, or the final schematic that Kairos is using for their concept. And you'll see it's a little simplified, but one of the pieces that you'll notice is not on this is any type of a storage system or anything else like that. And so Kairos did make some changes and some final decisions about how to alter the concept outside of that IRP, but it's something that, when you look at the overall impact of the IRP project, when you think about a workforce and a research impact, which is really what we look at when we think about, hey, was a project successful? Was it, did it contribute to the literature? Did it contribute to technology development? Did it increase or enhance the workforce in some way? These are some quick statistics, but there's 26 students that worked on this project that are now active members of Kairos Power's team. And the number that I heard from some of the PIs and co-PIs here is that when you look at faculty members today and national lab folks that are working in the Flibe Salt area, a lot of them are tied back to this project, the original concept of trying to purify these salts in a meaningful way. But there's a variety of students that have gone to work with other advanced reactor developers, including BWXT, TerraPower, and other molten salt reactor developers. And interestingly enough, when you look at other government investments in research and facilities that go to startups and to industry, this FHR concept has a demonstration award through the Advanced Reactor Demonstration Projects. to demonstrate a reactor concept by 2030. I believe it's going to be out at Oak Ridge National Laboratory as the facility, but yeah, that's that's SkyWest Power and the project that was here. I hope I explained it well enough, but I hope what I'm really hoping you all take away from this is, how from a university perspective, university program perspective, how some of these major projects are designed and executed in a way that creates these types of outcomes. I'll use another quick example and then I'll end and open up for some questions. But there's another interesting project that has a pretty long lifetime as well, but it's still ongoing. So this is going to be a little bit shorter of an explanation, but is another example of a completely different area that gives you a little bit different look of how some of these projects look. Now this project is a project by University of Michigan, talking about materials qualification using ion irradiation. And so the idea behind this project is, what if, and it's a what if, right? But what if we can use ion irradiation as a surrogate for materials testing? Goal of the project is to demonstrate the capability to predict the evolution of microstructural properties and characteristics in structural materials through ion irradiation. And obviously ion irradiation and neutron irradiation are different. They're different environments, they're different in a lot of different ways. But the idea is, can we use it as a surrogate? Can we find a way through experimentation to bridge the gap between ion and neutron irradiation? This is a project that started in 2013, and we just announced another IRP project that's going to hopefully complete the effort here. It's been about a 10-year effort to look at this problem, but the final report is on high fidelity ion beam simulations of high dose neutron irradiation, and you can look at the report on OSTI, and it's linked here when and if you do get a copy of this presentation. So this is really an integrated approach, very similar to when you look at the similarities between the last project and this. The idea was to use these IRP funds to fundamentally change Michigan's ion beam laboratory to a triple beam setup. So a new accelerator was put in, and I'll show you a schematic of the changes to the facility. But the idea was, you have to make it possible. You've got to make the conditions possible in ion irradiation to maybe get some data that can be, you can use a modeling approach to start to compare these and make some assumptions about what an ion irradiation would look like and what a neutron irradiation would look like, and try to match those two things together. In coordination with that ion beam laboratory upgrade, there was irradiated samples that came from Bor 60 in Russia to try to get the experimental data that you need on the same batch materials to be able to make that comparison, right? So the same type of materials going to the reactor that are getting irradiated through the ion beam facility. Obviously, got to have materials characterization, and then the idea was to use that data and try to understand how you get from A to B in a lot of different ways, and how you use modeling techniques to really overlap those two types of things, instead of understanding that the conditions are going to be different, temperature is going to be different, a lot of different factors are going to play into a reactor environment versus something like an ion beam facility environment. So this gives you an idea of the facility upgrades, and gives you an idea of what there's a lot of facilities that have this type of a setup that has an accelerator and several beam lines. Several lights coming off of it, and the idea here was a full expansion into a second target room to provide much different capabilities, including this right here, which is the the triple ion beam all coming into one area. So from a materials characterization standpoint, the idea was that ultimately the idea is, what if we can take 10 years of a neutron irradiation and compress that down into doing it in a day in an ion irradiation environment? That's the dream, right? If that could happen, that would have huge impacts and huge consequences for being able to rapidly qualify materials. So what they did is they had samples that were ion irradiated and also neutron irradiated, about 20 dPa. And they used several different techniques to try to characterize. They did in situ at IBEM, which is at Argonne National Laboratory, ex situ, which was more bulk ion irradiations that took place at the Ion Beam Lab. And then they, of course, had the Bohr 60 neutron irradiations, which, is a challenge in and of itself to get samples to Russia, get them irradiated and get them back. Both sets of samples were analyzed and compared using microstructural characterization techniques, and there's some similarity in the irradiation effects, and there were some differences, obviously, because of the environments they were in. There were some challenges they had, both making sure that the ion irradiations didn't have, they had some carbon impurities that were a challenge there. And obviously you've got your reactor environment, which is very complex and different. So really what the follow-on projects, not only was there additional data that was collected, but one of the interesting things about this project is there's some world-class data or some modelers that are really looking at cluster dynamic models to try to bridge the gap between those two different types of irradiation techniques. Like I said, there's a whole new project for 3 or 4 more years that is going to be addressing those types of issues while collecting additional data. And the real thing is can you bridge that gap? And I think that's still a very open question in this type of a project. It's one of those things that when you look at the research space and university research space, the idea is you're trying to discover and understand unanswered questions. And so this is an example of that, where although it's been lengthy, there's been a lot of really smart people working on this problem for quite a while, and we'll see what kind of research comes out of that project at the end of the day. So like I said, the new award focuses on the modeling effort, but additional data collection through irradiations, both at neutron and ion irradiations. And ultimately, when you look at the overall support for this project, it started in 2013, was supported through the materials, DOE materials program for a few years. And like I said, it's just starting an award here in October to really hopefully culminate a lot of the data that's been collected, and a lot of modeling that's been built thus far. So as a conclusion, the integrated research projects have really established a place in NEP's overall research portfolio. They've created a space for major innovation, things that when you look at a DOE investment standpoint, have some very clear, very high profile outcomes. To give you an idea, I highlighted 2 or 3 projects here. There's 28 IRP projects that have been either actively being completed to date or are finished. That's constituted about $105 million of the overall NEUP portfolio, that close to $1 billion of funding. And there's been 18 different lead institutions and numerous other partnering institutions. When you talk about these IRP projects, they're truly consortium style projects where you've got 3 or 4, maybe even 5 institutions involved. And with that is what I have for you all today. And I'd be interested in any questions you might have.
We good for our online participants. If you have any questions, please post them into the chat and we'll moderate them from here. We're waiting, we'll get questions from the room.
Thank you. I have some questions, comment. So it's an interesting story about Kairos Power, and there are other stories like NuScale as well. I mean, it's from beyond the 2011 timeline, but one of the things, just an idea, something you might want to consider for this type of talks. So I'm sure Kairos Power, after the original IRP, right, was part of several, right?
Mhm.
Regular projects as collaborators, right?
That's right.
And then, and so there was a sort of continuous, if not sort of direct, but a continuous support to. One example, I'm part of NIMS IRP, and Kairos is one of the industry partners, right?
Right.
We do, and then one also kind of support some of it. So it kind of just an idea, right? To say,
Yeah.
It's harder to see through, but you know, I'm sure, you know, government support continues to resolve some of the issues through many different projects as well, right?
Yeah, absolutely. That's a really good point. I did not, I made the decision not to go that deep into the space, but there are some really interesting results that happen on these smaller NUP projects that have actually had a really big impact on these type of reactor designs. An example I'll use that's finished, so I know there's some active projects too, but an example I'll use is University of New Mexico had an award, that's not concluded, that focused on twisted tube heat exchangers, which are actually being used in the FHR, the Kairos design. And so that's an example of something that was a much smaller award. That was functionally a different team that was collaborating with folks that were involved in the Kairos startup. That's been incorporated as well. So there's a there, when you think about the big, there's also a bunch of very small, I shouldn't say very small, but smaller parts that fit into that overall picture. That need to be recognized. You're absolutely right that there's contributions from a lot of different folks that lead to, you know, those final design decisions or the modeling that supports the overall concept. So yeah, well said.
And this type of thing, sorry, will help to present the overall DOE effort as not the 28 IRP project, which each of them is very important, right?
Yeah.
But then you say, okay, here's the company which is fingers crossed successful, right?
Yeah.
And then along the way, they get it.
Yeah, no, it's point very well made. Yep, absolutely. And I think that's a great illustration of how all the different research portions of the NUP and UNLP program fit. And there's examples not only on the small IRP projects, but also on, you know, I saw some fellows back here, but some graduate fellows who focus their research around some of these issues, who are either, you know, at molten salt reactor developers, FHR developers, or in academia who are in these types of roles for their proposing projects. They're really complementary to these types of concepts. So yeah, that's great feedback. Other questions?
I just wanted to make a comment. I think the faculty here at NC State, this is for your students, postdocs, and others, have really done an outstanding job of going after funding through our NEUP program over the years, not just recently, but NC State is in the top 5 for sure in terms of funding coming out of the NEUP program over the last 12 years or something. Even though we only have one IRP project, but still, that means we've got a lot of smaller projects over the years, and you saw the numbers. In fact, this year, I'm not going to say the exact numbers, but NC State had far and away more pre-applications that went in, probably due to stimulation to faculty than any other university in the country, for sure. So no pressure. No pressure on NC State.
Quantity conducts the quality.
Quantity has to translate into quality too, as we do our panels. Panels are different these days. We've changed a little bit. Things are a lot more open, more academic. Reviewers, if you will, and people sitting on the panel. So it's quite a bit more open. But NC State has really done their part. The faculty here in the department, as well as other departments. There's material scientists, mechanical engineers, others submitted to the same program. So congratulations.
Hey, go ahead.
Thank you for the presentation. My question is, do you have any restriction on the commercialization of the output of the project?
So the conditions of the NUP awards, they're intended to, even though they might have an applied aspect to them, they're intended to be publishable, to be open research, right? If that resonates, what I'm trying to say there. There are some specific conditions where, things can be commercialized and that's encouraged, but for the most part, it's open research, not proprietary in any way. And from a commercial, to answer your question directly from a commercialization perspective, that's part of this environment, right? Is if there's a technology that's been developed that can be commercialized, that would be an opportunity.
Let me just say. The usual rules apply. The universities
That's right.
own all the IP that come out of their projects, as usual, okay? So you're free to, the university develop those projects into commercial entities, and spin-off companies, or license your inventions to bigger companies and so forth. And that does happen. And of course, Drew also has in his portfolio the SBIRs and STTRs that DOE does in the space. So there is support there for people that do want to commercialize. There's a pathway forward there if you want to do that, but that's up to you, up to individual faculty. It's interesting, the state of North Carolina is just going to institute a new fund for commercialization of intellectual property coming from the universities in the state. And it includes all different areas, not just everything. But it's a great opportunity, I think, for students and faculty to get together and propose a new startup company, get some funding from this fund that might be available. And certainly we've had a number of students as well as faculty put together companies, start off, be very successful here and around the world. So it can happen.
Oh, any questions online? Don't be shy. Go ahead and post them on the chat. You could be the first one this year because you've been pretty quiet so far this year. Last year was pretty impressive, so I was kind of hoping to get a few more this year. We'll see how it goes. While we're waiting for you to get over your internet shyness, any more questions from inside the room?
Wi-Fi doesn't work on campus, let me explain.
No,
Yeah.
So, and in the presentation, I have a small question about irrigation experiment. So, are there any near-term irrigation experiments for like DOE-Q2 or UM or UC or any near-term advanced fuel concepts?
Yeah, I don't know that I can comment any like educated detail about, I think the short answer is yes, that there are projects that are being proposed in that space. I'm not directly aware of any active experiments that are happening, but those types of fuels experiments, there's the advanced test reactor and others, they're testing fuels and other structural materials that are outside the fuel space, but take my card and I'll pass it on to the metallic fuels folks that I know at Idaho National Laboratory, and they might be able to answer your question in a more educated way. Yeah, thank you.
I have a comment on all of the graduate students. At some of the conferences, the NS conferences, we've introduced the concept of elevator pitches. You have a few minutes to present your research, right? Research that you own, and hopefully you know everything about before, current, and hopefully the future. So now you have a set of years in charge of a program with a lot of millions of dollars. And this is your opportunity to showcase what you're working on and what you're passionate about. After the seminar, I invite you to sit down and do it. If it's the first time you're doing it, you may be shy, but I still encourage you to do it. If it's the 5th time you're doing it, you hopefully have a lot more confidence.
And I'll add to that, it's probably the best part of this job is to hear what all you're working on. So it's, when you think about, some of the stuff that John was talking about coordinating thousands of reviews in a really short time period, there's some really stressful pieces to try to administer this type of a program, but that, you know, seeing all of you, seeing the research that you're doing, seeing the outcomes that you're getting, what your careers are gonna be in the future is what drives those of us to do this. So, I'd love to hear that type of stuff. You reminded me though, I also wanna plug this, is that we have a newer program. It's a reimagined program. It's called the Innovations in Nuclear Energy Technology Student Competition. If you are publishing papers in journals or peer reviewed conference proceedings, where you are the primary author, there is a competition that we run that provides honoraria and travel opportunities to different conferences to be able to highlight your work, not only highlight the paper that you've submitted, but highlight the follow-on work that you've had. And so we're taking a cohort of 6 or 7 graduate students to the Winter A&S meeting in Washington, DC this year, who were awarded these honoraria last year, not last year, but in March. And I would encourage you, if you've got papers that are sitting on, that are accomplishments that are now sitting on your CVs, look at those, see if they meet the requirements, if they're in the Office of Nuclear Energy's technical area, for submittal to that competition. It's anywhere from $1,500 to $3,500 honoraria and travel opportunities. And so we're doing a mix of in-person presentation opportunities and virtual presentation opportunities that will be advertised through our NUP contacts and hopefully through groups like ANS and other groups like that. So just that's a plug, as well. Just, you don't only have to pitch it. You've got a paper. We'd love to see those papers and love to recognize the hard work that you all have been doing as well.
I think NC State had 2 second place winners this last round, at least 2. John Crozier was one I was talking to before. And so he would have gotten that money to, attend a conference and do anything that he wants to with it. But you're right at that level. Any published paper that you have that you've done in the last year is eligible to be submitted to that competition. And you compete very well.
Any more questions? Going once? Going twice? Always on twice? No, nothing on twice? Nothing online? Then let's thank our speaker one more time.
Listening to at 5:30, there's a ANS Vision chapter meeting, and the program is being highlighted from the perspective of what they have to offer. It's highlighting